Hello, welcome all. Myself, Dr. Mukesh Kadam, Department of Chemistry, LGMSS College, Mandangarh, Ratnagiri. First of all, I thanks MMTTC, University of Mumbai, and Doshi Vakil, Art Commerce Science College, Goregaon, for organizing short-term course on e-content development for all faculty members of nearby Ratnagiri, Sindhudurg and Raigad colleges. Now, here my topic of presentation is coordination chemistry and overview of complex ligand and crystal field theory. Now, the coordination chemistry plays a very important role in catalysis, bioinorganic and organic synthesis field. The best example of coordination complexes are hemoglobin, chlorophyll and other part which shows a coloration. The introduction to the coordination chemistry, the definition. The coordination chemistry is a study of compound that consists of central metal ion and surrounding the molecule anion known as ligand. In a coordination complexes, there are two types of part. First is central portion, which is generally transition series metal ion, and outside portion, which is a ligand, which is a negatively charged, or sometime in case the ligand may be neutral. The ligand is electronically rich with having ability to donate pair of electron to the central vacant d orbital of the metal atom to form a coordination complexes. This is the simple definition. What is the importance? Generally, all coordination complexes used in a field of organic synthesis, in a field of medical for synthesis of various organic compound, pharmaceutical compound, or sometime it also used as bioinorganic catalyst for the synthesis. The example of the coordination complexes is well known. The hemoglobin present inside the human body, which plays a very important role, which acts as a blood transportation system, which transport the oxygen from lungs to other body part. This hemoglobin is the best example of coordination complexes. Another example is chlorophyll pigment is also a coordination complexes, in which magnesium as a central metal atom. Here, key terms in a coordination complexes: central metal ion. Generally, central metal atom is the transition series metal ion, or metal belong to the first and second group. Is also shows the ability to form coordination complexes because they having a enough vacant s, p and d orbital for the formation of coordination complexes. That's why typically transition metal ion, Ap dipositive and copper dipositive and other well known first, second, third transition series metal atom also shows this type of ability. What is ligand? Ligand is a negatively charged central metal atom which having ability to form coordinate bond. The main condition, ligand must be electronically rich and which having ability to donate the electron. And coordination number is another important term in a coordination complexes. What is coordination number? The coordination number is a simple term. How many ligand atom present in a coordination sphere? What is coordination sphere? Coordination sphere is the central metal atom including ligand and total number of charges present on the central metal atom along with charges present on the square bracket. Now this coordination number is depend upon, for example, a coordination complex which having 4 ligand atom, which is a tetrahedral or square plane, which having coordination number 4. Another example, for example, in a coordination complexes there are 6 ligand atom. At that time, the coordination number of such coordination complexes is 6. Now this coordination number is very important. Here we ask one question to our viewers. What is the coordination number of coordination complexes? Types of ligand atom. The ligand also having a type. The ligand may be monodenated, bidenated or polydenated ligand atom. the ligand which having ability to form a number of coordinate bond to the central metal atom. Some metal atom forms coordination complexes with monodenated ligand atom. In this case, ligand forms only one coordinate bond. But bidenated coordination complexes in which ligand at a time forms two coordinate bond with the central metal atom. At that time, such a ligand atom form a ciliate ring around the central metal atom. Generally, monodenated coordination complex, when we compare the stability with bidenated or polydenated coordination complexes, in this case, bidenated and tridenated or polydenated coordination complexes show the greater stability. Coordinate bond. Generally, coordinate bond formation takes place in a electronically deficient species and electronically rich species. The best example, central metal atom and ligand atom forms a coordinate bond. The best example of the coordination complex is Cu NH3 taken 4 times dipositive. Here, dipositive is the total number of charges present on the square bracket. Sometime in a neutral ligand atom containing coordination complexes, this dipositive is itself considered as the oxidation state of central metal atom. Now here, in a coordination complexes, metal atom is copper, NH3 is a ligand, and dipositive is a oxidation state. Means every metal atom shows a oxidation state. Generally, transition series metal atom shows variable oxidation state. Due to variable oxidation state, they forms different types of coordination complexes, from bidenated or coordination number 2 coordination complexes to coordination number 7 coordination complexes. This type of coordination complexes generally formation takes place through the transition series metal atom. Another important point of the coordination chemistry is the beauty of coordination chemistry. Here, look at this. The complex influence on color. Generally, all transition series metal ion, when they form a coordination complex, at that time they show the coloration phenomena. The beautiful example here, ApH2O6 tripositive coordination complex shows different color. COH2O6 dipositive coordination complex shows red wineish color. NiH2O6 dipositive coordination complex shows greenish color. Copper coordination complex shows blue color, and zinc coordination complex shows colorless or it is transparent. This beauty is a coordination complex is because of transition of electron from d orbital to d orbital. The unique property of all transition series metal ion coordination complexes is to show the transition of electron from d to d. That means the electron generally transit from d orbital to d orbital. Due to this phenomena, the coordination complexes shows coloration. Another the important point of this presentation is the crystal field theory. The important point. Previously, there are so many theories introduce geometry, coloration, magnetic behavior of the coordination complexes, but they fail to explain some unique property of the coordination complexes. That's why here the crystal field theory is a huge importance in the coordination chemistry. The crystal field theory explains low spin and high spin ability of the coordination complexes. Due to this phenomena, due to this importance, the crystal field theory considered in my presentation. The crystal field theory explain the behavior of metal ion in a coordination complexes by splitting or by considering the splitting of a d orbital of the central metal atom. Other theories cannot give so much importance to the d orbital of the central metal atom, but crystal field theory only focus on the nature, behavior and splitting of the d orbital. Here, due to this, here we consider the importance of crystal field theory. Helps to understanding color, magnetic behavior and stability of the coordination complex. These are the very important phenomena of the coordination complexes. Here crystal field theory explain the magnetic behavior if coordination complex is paramagnetic or diamagnetic. The coordination complexes can show stable or unstable. There are so many coordination complexes are unstable. they are easily undergo a redox reaction, oxidation reduction reaction. Sometimes this was a ligand exchange reaction, but this theory, crystal field theory, explain the stability of the coordination complexes. That means the coordination complex is stable or unstable, or the coordination complexes show such type of chemical reaction on the basis of their ligand action, which is lability or inertness of the coordination complexes. Now here the crystal field splitting is an important phenomena in octahedral, tetrahedral and square planar coordination complexes. Here crystal field splitting of octahedral coordination complexes. First of all, here central metal atom, when present in its individual gaseous state, at that time all 5d orbitals present in a degenerate energy level. Their degeneracy remain as it is, means they are having a equal energy level. But when the interaction of this central metal atom takes place with the ligand orbital, at that time what happens, the crystal field splitting takes place. This d orbital undergo crystal field splitting, and this crystal field splitting generally split into two sets. First set is Eg set and another is the T2G set. Here in octahedral coordination complexes, crystal field splitting is different than that of the tetrahedral coordination complexes. In octahedral what happens, Eg set orbital goes to the higher energy level from the very center, and T2G goes to the lower energy level from the very center. Now this is the crystal field splitting diagram of the octahedral coordination complexes, in which dx square minus y square and dz square orbital goes to the higher energy level, and dxy, dyz and dxz orbital goes to the lower energy level. The important phenomena is that here dxy, dyz and dxz orbital goes to the lower energy because of these orbitals present in between the axes. There is less interaction takes place with the ligand orbital, because ligand come towards the central metal atom through a fixed Cartesian coordinate, and when metal interact with the ligand atom through a fixed Cartesian coordinate, that means those orbitals present on the axis are more interact with the ligand orbital, and due to this more interaction, those orbitals present on the axis, which are dx square minus y square and dz square orbital, directly face to face interact with the ligand orbital. That's why their energy increases from the very center, and which goes to the higher energy level from the very center. Now here the T2G and Eg is a crystal field splitting. T2G goes to the lower energy level by minus 4 dq, and Eg orbital goes to the higher energy level by plus 6 dq. This is the crystal field splitting parameter of the octahedral coordination complexes. In octahedral coordination complexes, another important phenomena is that there are 6 ligand atoms. That means in octahedral coordination complexes, the coordination number is 6, and due to 6 ligand atoms, the crystal field splitting is different than that of the tetrahedral coordination complexes. Thank you listening me. Thank you so much.